Good day. My name is Chandler M. Manlongat from CM124-1B12 under of Dr. Catlia de Castro Cruz. So today I'm going to be discussing about the introduction to spectroscopy, and I'll be answering 24-8 and sample problem in the PowerPoint of Intro to Spectroscopy. According to Hanson et al., spectroscopy is generally defined as the area of science concerned with the absorption, emission, and scattering of electromagnetic radiation by atoms and molecules, which may be in the form of gas, liquid, or solid phase. So, when we say spectroscopy, it has something to deal with radiation and matter. So, spectroscopy played a vital role in the development of modern atomic theory. It provided perhaps the most widely used tools for elucidation of molecular structure, as well as the quantitative and qualitative determination for both inorganic and organic compounds. Spectroscopic methods can be classified according to the region of electromagnetic spectrum used or produced in the measurement. So for the electromagnetic spectrum, it consists of gamma ray, X-ray, ultraviolet, visible light, infrared radiation, microwave, and radio frequency. So as you can see here, we have here a chart of electromagnetic spectrum that varies from its frequency and wavelength. So the higher the frequency, the shorter its wavelength. And vice versa. So it has a relationship of inversely proportional. So for electromagnetic radiation, it is a form of energy that is transmitted through space at enormous velocity. It can be described as wave with properties of wavelength, frequency, velocity, and amplitude. In contrast to sound waves, light requires no transmitting medium. Thus, it can travel readily through vacuum, and light also travels nearly 1 million times faster than sound. So for the wave properties, in dealing with phenomena such as reflection, refraction, interference, and diffraction, electromagnetic radiation is conveniently modeled as waves consisting of perpendicularly oscillating electric and magnetic fields. So for the properties of wave, we have here amplitude, wherein it is the maximum displacement of a particle. Here, it is measured in meters, wherein it is a vector quantity that provides a measure of the electric and magnetic field strength at the maximum in the wave. Next property would be wavelength. So wavelength is a length of one full wave, the distance between the two adjacent points on a wave with the same phase. So the wavelength is the linear distance between the successive maxima or minima of a wave. So it has this symbol measured in meters. Next property would be time period. So it is defined as the time it takes for one full wave to occur. It has this symbol T measured in seconds. So the period of an electromagnetic wave is the time in seconds for successive maxima or minima to pass a point in space. So lastly would be the frequency. So when we say frequency, it is the number of full waves per second. It has this symbol, small letter f, measured in hertz. So the frequency of an electromagnetic wave is the number of oscillations that occur in 1 second. So the product of the frequency in waves per unit time and the wavelength in distance per wave is the velocity of the wave in distance per unit. So note that both of both of the velocity and the wavelength depend on its medium. Corresponds with this equation. The electric field for a single frequency wave oscillates sinusoidally in space and time. Note that the direction in which the field oscillates is perpendicular to the direction in which the radiation propagates. So for the speed of light, in a vacuum, light travels at its maximum velocity. This velocity, which is given with the special symbol c, corresponds with 2.9972 times 10 raised to 8 meter per second. The velocity of light in air is only about 0.03% less than its velocity in vacuum. Thus, for vacuum or for air, the equation can be written as speed of light is equal to frequency in hertz times the wavelength is equal to 3.00 times 10 raised to 8 meter per second is equal to 3.00 times 10 raised to 8 centimeter per second. Wherein in the medium containing matter, light travels with the velocity less than c because of the interaction between the electromagnetic field and the electrons in the atoms or molecules of the medium. For the wave number, so it is another way to describe the electromagnetic radiation. So it is defined as the number of waves per centimeter, and is equal to 1 over wavelength. And by definition, wavelength has the units for centimeter raised to negative 1. So for question 24-8, we have here a problem of a sophisticated ultraviolet visible near infrared radiation instrument has a wavelength ranges from 185 to 3000 nanometer, wherein this 185 is the minimum range and this 3000 nanometer will be our maximum range. So we are asked to find its wave number and frequency ranges. So solution, we are required to use the formula for wave number, which is wave number is equal to 1 over its wavelength, wherein wave number corresponds with the symbol and wavelengths correspond with this symbol in centimeter. So for the minimum range, we are given with 185 nanometer wavelength, and we are asked to find its wave number. So we're going to be using the formula for wave number. 1 over wavelength is equal to 1 over 185 nanometer. Because the unit is in nanometer, we're going to convert it first to centimeter. Because by definition, wave number has a units of centimeter raised to negative 1. So we're going to multiply it with 10 raised to negative 7 centimeter over nanometer. So nanometer would cancel out. So our resulting value for the wave number and minimum range of frequency is 5.41 times 10 raised to 4 centimeter negative 1. So this would be our minimum frequency range. So for the maximum range, we have 3000 nanometer wavelength. So we are asked to find the wave number. We're going to use again the formula. 1 over wavelength is equal to 1 over 3000 nanometer. Because its unit is in nanometer, we're going to convert it into centimeter. So we're going to multiply it with 10 raised to negative 7 centimeter over nanometer. So nanometer would cancel out. So the resulting value would be 3.33 times 10 raised to 3 centimeter negative 1. So this would be our wave number and maximum frequency range. So the answer for our question, so the wave number from 185 nanometer wavelength, it corresponds to 5.41 times 10 raised to 4 centimeter raised to negative 1. So for 3000 nanometer wavelength, the wave number is 3.33 times 10 raised to 3 centimeter raised to negative 1. So the frequency ranges from 5.41 times 10 raised to positive 4 centimeter raised to negative 1 to 3.33 times 10 raised to 3 centimeter raised to negative 1. So for the next question, from the sample problem in the PowerPoint of Intro to Spectroscopy, so a solution contains 4.50 ppm of a colored species. It is found to have an absorbance of 0.30 at 530 nanometer in a 2.0 centimeter cell. So we are asked to calculate the absorptivity. So first, let's have a glimpse on the absorption process. So the absorption law, also known as Beer-Lambert law or just Beer's law, tells us quantitatively how the amount of attenuation depends on the concentration of the absorbing molecules and the path length over which absorption occurs. So, a slight reverse a medium containing an absorbing analyte, the intensity decreases as the analyte becomes excited. So for an analyte solution of a given concentration, the longer the length of the medium through which the light passes, path length of light, the more absorbers are in the path, and the greater the attenuation. So similarly, for a given path length of a light, the higher the concentration of absorbers, the stronger the attenuation. So for the transmittance, it is the fraction of incident radiation transmitted by solution. So it has this equation. Transmittance is equal to light leaving the sample over light entering the sample. So transmittance is often expressed as a percentage and called as the percent transmittance. So percent transmittance is equal to light leaving the sample over light entering the sample times 100%. So absorbance can be calculated from percent transmittance as follows. So T is equal to percent T over 100%. And absorbance is equal to negative log T is equal to negative log percent T plus log 100. and it is equal to 2 minus log percent T. For the transmittance and absorbance, the absorbance A of a solution is related to the transmittance in a logarithmic manner. It has this equation: A is equal to negative log transmittance is equal to negative log P over initial P is equal to log initial P over P, wherein this initial P corresponds with the light entering the sample, and this P corresponds with the light leaving the sample. This thing. So according to Beer's law, absorbance is directly proportional to the concentration of the absorbing species, C, and to the path length, B, of the absorbing medium as expressed by absorbance is equal to log initial P over P is equal to A times B times C, wherein letter A is proportionality constant called absorptivity, and B is the path length, and C would be the concentration of absorbing species. So because absorbance is a unitless quantity, the absorptivity must have units that cancel out the units of B and C. When we express the concentration in moles per liter and B in centimeter, the proportionality constant is called the molar absorptivity and is given by this symbol. So the equation is absorbance is equal to molar absorptivity times path length in centimeter and concentration in moles per liter, where the molar absorptivity has the units of liter per mole times centimeter. This. So in the sample problem in the PowerPoint, we're going to use the Beer's law to find the or to calculate the absorptivity. So the formula is absorbance is equal to log of initial P over P is equal to absorptivity times cell path length times the concentration. So for the sample problem, the PowerPoint of Intro to Spectroscopy, we are asked to find for the absorptivity. So for the solution, we're going to use the Beer's law. Absorption is equal to absorptivity times cell path length times the concentration. So our given absorption is equal to 0.30 ABS, and for the absorptivity, this is the one that we're going to calculate. So for cell path length, this is equal to 2.00 centimeter, and our concentration is equal to 4.5 ppm. So in order for us to calculate for the absorptivity, we're going to manipulate this formula. So rewriting this formula, absorption is equal to absorptivity times cell path length times the concentration. We're going to multiply it both sides by 1 over cell path length times the concentration. So this would cancel out. So our working equation, absorptivity is equal to absorption over cell path length times the concentration. So substituting the given values, so 0.30 ABS over 2.00 centimeter times 4.5 ppm. So our absorptivity is equal to 0.033 ABS per centimeter ppm. So this is our absorptivity. So the answer for this question, the absorptivity is 0.033 ABS over centimeter ppm. So the reference as follows. Thank you for listening and God bless.